Jai Hind everyone. Today I am going to discuss properties of Fourier transform. Subject name is network analysis and synthesis. Subject code is KEC 303. So Fourier transform is basically a mathematical tool that we use in electrical circuit or analysis. Okay. So by using this transform, we can convert signals or functions from time domain to frequency domain. So today we will discuss this. What is Fourier transform? What is Fourier series that we had discussed earlier. So now we will continue and we will see the difference between series and Fourier series and Fourier transform, and we will see the properties of Fourier transform as well. So Fourier transform is the input tool that is used to decompose an image into its sine and cosine components. Okay, so basically it is a mathematical tool and mathematical transform that decomposes any function depending on time or space into function depending on spatial or temporal frequency. Okay, so as I told earlier that this Fourier transform converts function or signals from time domain to frequency domain, and that depends on if it is function of time, then it will convert into frequency, and if it is the function of space, then it will convert that into the spatial frequency. Okay, so such as the expansion of musical chord in terms of volumes and frequency as its constituent notes. Okay, so musical signals or musical chords can be written in terms of frequencies and its constituent notes by using the Fourier transform. Okay, so the term Fourier transform refers to both the frequency domain representation and the mathematical operation that associates the frequency domain representation to a function of space or time. Okay, so we will see. So first, what is the continuous time Fourier transform? That is also known as the Fourier integral. So continuous time Fourier transform or Fourier integral, we will see what is this. So Fourier integral, we represent this as ft of function ft as summation of Cn e to the power j n omega naught t, n equal to minus infinity to infinity. Okay, so here Cn, that is the coefficient of Fourier, is Cn equal to 1 by t integration ft e to the power minus j n omega t dt over minus t by 2 to t by 2. T is the capital T, here it is the time period. Okay, so omega naught, that is the fundamental frequency, and we can write this as omega naught is 2 pi by t. Okay, so if we put this value into this expression, then ft we can write 1 by t integration minus t by 2 to t by 2 ft tau e to the power minus j omega n omega naught tau d tau e to the power j n omega naught t. Okay, so this is the way we will proceed for the derivation. So here omega naught is 2 pi by t. So if we assume del omega naught equal to omega naught, that is 2 pi by t, so then in this expression we can see if t tends to infinity, del omega will tend to 0. Okay, so that's why we had integrated this in this way, and then we will receive this function. Okay, so ft. Okay, so this is the Fourier integral, formula for the Fourier integral. So here 1 by 2 pi integration minus infinity to infinity, in bracket we had written here, this is the f of j omega. Basically this is representing f of, what is f of j omega? F of j omega, that is the Fourier transform of function ft. Okay, so we can write this as ft e to the power minus j omega t dt minus infinity to infinity. This is the formula for the Fourier transform, and here we can write Fourier integral ft as 1 by 2 pi minus infinity to infinity f of j omega e to the power j omega t d omega. Okay, so here function will be given, Fourier transform will be there in frequency domain, and by using Fourier integral here we can convert that into the time domain as well. Okay, so this is the formula that we use in synthesis, in network synthesis. Okay, so here this is the Fourier transform that we will use in the analysis of the given network. Okay, so this will be used for the designing purpose, designing any network or system, and this will be used for the analysis purpose. So this is the Fourier transform and this is the Fourier integral. Okay, So now we will see Fourier series versus Fourier integral. Okay, so here Fourier, this is the generalized formula, you can say, or exponential form of Fourier series. Okay, that we had discussed in our earlier lecture. So here Fourier series we can write as ft equal to summation of Cn e to the power j n omega naught t n equal to minus infinity to infinity. This is representing the Fourier series in exponential form. Okay, so here Cn is the Fourier coefficient, okay, complex Fourier coefficient or exponential form of Fourier coefficient. Okay, so if function ft is given, we can derive this coefficient. Okay, so there is other form for Fourier series also, that is the trigonometrical form. In that form we derive a naught, an and bn. Okay, so these three coefficient needed to be derived in if we need to write the Fourier series in trigonometrical form, but this is the exponential form. Okay, so it is a periodic function, and by using this Fourier series we draw discrete spectra. Okay, so if we plot magnitude of Cn, okay, if we plot magnitude of Cn versus frequency, okay, omega versus Cn, then we will be having the magnitude discrete spectra, and if we plot omega frequency versus phase, okay, then we will be having phase discrete spectra. Okay, so this is the periodic function, and here this is the Fourier integral. So by using the Fourier integral, first we have to write the Fourier transform, that is f of j omega, and by using this is the non-periodic function. Okay, so using Fourier transform we can draw continuous spectra. Okay, so we should remember, by using Fourier series we can draw discrete spectra, and by using Fourier integral, Fourier transform, we draw continuous spectra. Okay, because this f of j omega will be the function of omega, and we will be having two terms, magnitude and phase, as we see in complex number term. Okay, complex number. So similar to that, f of j omega will be having magnitude as well as phase. So if we will plot magnitude versus frequency versus magnitude of f of j omega, that will be continuous magnitude spectra, and if we draw frequency versus phase of f of j omega, that will be the continuous phase spectra. So now what is inverse Fourier transform? Okay, so this is also known as the inverse Fourier transform. F of j omega will be given, we will calculate ft. Okay, so this is the formula for the inverse Fourier transform, and this is the formula for the Fourier transform. Okay, so these two are called as the Fourier integral pair. Okay, so inverse Fourier transform will be used for synthesis, and Fourier transform is used for the analysis purpose. Okay, so now what are the conditions that must be satisfied for existing the Fourier transform of any function? So first condition and sufficient condition is that ft should be absolutely integrable. Okay, so that means integration of ft should exist. Okay, so it should not be infinite, it should be having some finite value. So then only there will be Fourier transform of that function. Okay, so now we will see how we will draw continuous spectra by using the Fourier transform. As we had seen in discussion of Fourier series, that by using Fourier series we draw discrete spectra. Similarly, by using Fourier transform we draw continuous spectra. How, that we will see. See, if function ft is given, you can easily calculate f of j omega. So this is the Fourier transform of ft. Okay, so Fourier transform of ft. Okay, so now see, if you calculate this will constitute of two part. One part of this will be real part and another part will be imaginary part. Okay, so now you can calculate the magnitude also. Okay, so this is the rectangular form of f of j omega. So you can write this in the polar form as well. So this is the f of j omega in polar form. F of j omega is magnitude into e to the power j phi omega. Okay, so this phi omega is representing the phase of this f of j omega. So that will be tan inverse. So you can write phi omega as tan inverse imaginary part of j omega divided by real part of j omega. Okay, so magnitude of f of j omega, so it is very easy, like we do in case of complex number. F r j omega square plus f I j omega to the square and square root of whole this. So this is the magnitude, this is the phase. Now you can easily draw the spectrum. Okay, so here for example, if we take ft as 1, so ft if you write 1, okay, so then f of j omega will be 1 into e to the power minus j omega t dt. Okay, and we are taking range of the function from minus infinity to minus 1 to 1 only. The function ft, this function in mathematical form can be written as ft equal to 1 when t is ranging between minus 1 to 1. Okay, so and for rest of the time it is 0 when t is greater than 1 and when t is less than minus 1. Okay, so this is the graphical representation of this function. Okay, so now if we need to derive the Fourier transform, we can write 1 e to the power minus j omega t, and we will put limit as minus 1 to 1 because function is existing only between minus 1 to 1. So it will be integration of this will be minus 1 by j omega e to the power minus j omega t minus 1 to 1. So here this is the Fourier transform of this given function. Okay, so now you will have to, if you need to draw the spectra, that means if we calculate the magnitude of f of j omega, obviously that is the function of omega only. Okay, see, so here we can write graph of, see what is the function, f of j omega is 2 sin omega by omega. Okay, so f of magnitude f of j omega is 2 sin omega by omega. Okay, so that means its magnitude is 2 into sin omega by magnitude of this. Okay, so here it is 2 sin omega by omega, and we know graph of sin omega by omega is like this. Okay, and if 2 will not be there, it will be starting from 1. Okay, maximum value will be 1, but only here it is multiplied with 2, so magnitude will be at 2 only, maximum. Okay, so similarly for the phase also you can plot. So this is the magnitude continuous spectra and this is the continuous phase spectra. Okay, so this is the way in which by using Fourier transform we draw continuous spectra. So now if we take example of exponential, here what is the function ft is e to the power minus alpha t, okay, when t is greater than equal to 0 and 0 when t is less than 0. Okay, so now if we need to derive the Fourier transform, here in place of ft you will write e to the power minus alpha t and limit will be from 0 to infinity because function is not existing here. Okay, so here limit has been changed. Now after integration and after putting the value of limits, this is the f of j omega that you are receiving. Okay, so now you need to draw the spectra. Okay, so what is the magnitude here? So here magnitude, see, f of j omega as, see here it is 1 upon alpha plus j omega. So it is 1 upon alpha plus j omega. So magnitude of f of j omega is 1 upon alpha square plus omega square. So now as omega will increase, the magnitude will decrease. Okay, so it will be having maximum value at omega equal to 0. So at omega equal to 0, it is having the maximum value, and as omega is increasing, it is decreasing. Okay. Also, for omega equal to -2 and for omega equal to 2, it will be having the same value because it is the function of omega square only. Okay. So now if we see the phase of f of j omega, so here it is minus tan inverse omega by alpha. Okay, because for this phase is 0, 0 minus this. So now this is the function of tan inverse. Okay, tan inverse omega. So this is showing the graph of tan inverse only. Okay, and this is for f of j omega. So this is the way, by using Fourier transform, we draw continuous spectra. So now what is the property? What are the properties of the Fourier transform? So Fourier transform, first property is that, this is the general notation that I have assumed for explaining the properties, that function of ft is given and Fourier transform of that is ft. Okay. So Fourier transform of ft is f of j omega. So this is the linearity property, that two functions f1 and f2 are given and it has been multiplied with constants a1 and a2. So now Fourier transform of this whole function will be a1 f1 j omega plus a2 f2 j omega. f1 j omega is the Fourier transform of f1t and f2 j omega is the Fourier transform of f2t. So now second one is the scaling property. Here scaling means time is being multiplied with constant. Okay, so that a may be positive, that a may be negative. So f of at, here ft, Fourier transform of ft that I have assumed is f of j omega. Then Fourier transform of f of at will be 1 by mod a f of j omega by a. By seeing this property, we can see multiplication in time domain. Okay, multiplication of function in time domain with constant is division in frequency domain by the same constant. Okay, so this is very important property. We can prove this also. How we can prove this? Okay, suppose I am just proving this. Suppose let u equal to a into t. That means du equal to a into dt. So now you have to calculate Fourier transform of f of at. So you will write minus infinity to infinity f of at e to the power minus j omega t dt. Okay, so in place of at you can write u. Okay, so but as t tends to minus infinity, you will also tend to minus infinity, and as t tends to plus infinity, you will also tend to plus infinity. So there will be no change in limit. We can change the variable, okay, without changing the limits. See here, so it is minus infinity to infinity f of u, okay, e to the power minus j omega. In place of t equal to u by a. Okay, so you can write u by a, and in place of dt you can write a into du by a, du upon a. Okay, so simple. So now see here, if you take 1 by a outside, it is minus infinity to infinity f of u e to the power minus j omega u upon a into du. So now in place of t, if you see here, u is written. Okay, so now you can write this as 1 upon a f of j omega upon a. So this is the proof for the scaling property. So in similar way you can prove other properties also. So next is the time reversal. Here proof is already shown here. So Fourier transform of ft is f of j omega, then Fourier transform of f of minus t is f of minus j omega. So this is the way we can prove this. Okay, so Fourier transform f of minus t, it is written over here. So now only what you can do, you can assume minus t as another constant and then limits will be changing only. So ultimately you will receive this. Okay, so this proof is already given here. So next is the time shifting property, f of t minus t naught. Any function in time domain can be shifted in backward and forward as well. So suppose function ft is given. This is the function ft. Okay, so you can shift in this way, you can shift in this way. Okay, so in both direction you can shift t plus t naught, t minus t naught. Okay, so this is t minus t naught, this is t plus t naught. So now f of t minus t naught will be f of j omega into e to the power minus j omega into t naught. Okay, so here this is the proof. Okay, so t minus t naught e to the power minus j omega t dt. So now if you take t minus t naught as other constant, so you can write ft t plus t naught is minus infinity to infinity f of t minus j omega t plus t naught d of t plus t naught and all. So it will be e to the power minus j omega t. Again you are having the same value, so e to the power minus j omega t naught into f of j omega. Okay, so now this is the modulation property or frequency shifting property. So here in time domain, function ft is being multiplied with other function e to the power j omega naught t. Okay, another signal, you can say exponential signal is being multiplied with ft. Then what is the Fourier transform of new function modulated signal? So it will be shift of omega naught in frequency domain. So here f of, see, you can find this as reversal also. Here in frequency domain, in time domain, we are multiplying function with e to the power j omega naught t, and reflection is that frequency is being shifted by omega naught. Okay, in frequency domain. And prior to this, we had seen if we shift function in time domain by t naught, then in frequency domain it is being multiplied with e to the power j omega t naught. Okay, so this is the proof for this also. So ft e to the power j omega naught t e to the power minus j omega t. So now ft e to the power minus j omega minus omega naught dt. So this is nothing, this is the ft f of j omega minus omega naught. So this is the symmetry property, f of j t. Okay, so Fourier transform of f of j t is 2 pi f of minus omega. Okay, so 2 pi ft, 2 pi, this is the integral property that ft we had seen. Ft is 1 upon 1 by 2 pi integration minus infinity to infinity f of j omega to the power j omega t. So now you can write f 2 pi into ft as this. Okay, so now if we take 2 pi f of minus t, so instead of t you just need to write the minus t in this part also. So 2 pi f of minus t is this. So by interchanging the symbol omega and t, okay, so you can write, if you just interchange the sign, so instead of t you write omega here, and instead of t here you can write the dt. So you will be receiving this. Okay, so this is the symmetry property of Fourier transform. So Fourier transform of real function. Okay, so if function ft is a real function, that means f of j omega is having two parts, then f of minus j omega is the complex conjugate of f of j omega. Okay, this is the Fourier transform for real function. Okay, so f of minus j omega means Fourier complex conjugate of f of j omega. So here this is the f of j omega. Okay, ft e to the power minus j omega t dt. So complex conjugate of this we can write, so minus infinity to infinity f2 e to the power j omega t dt. So this is f of minus j omega. So this is the, here if function is having two parts and one is odd, one is even, then magnitude spectrum of f of j omega is even and phase spectrum of phi omega is odd. Okay, because see, this is the real even function. Okay, and this is the odd function. Okay, so that means if we plot, then magnitude spectrum will be even because it is the real part is even, and phase spectrum of f of j omega will be odd because imaginary part is odd function. Okay, So see here, so when ft is real and even, that means f of j omega is real. When ft is real and odd, okay, so then f of j omega is purely imaginary. So these are the proof for this. Okay, so here ft equal to f of minus t, that means function is even. So f of j omega is equal to f of minus j omega. So in this case it is for the real function, and this is for the real and odd function, that f of j omega will be purely imaginary. So see the example here, Fourier transform of ft is f of j omega. Then what is the Fourier transform of ft into cos omega naught t? Okay, so now see, solution is that ft can be written as ft into cos omega t. We can write cos omega naught t as 1 upon t e to the power j omega naught t plus e to the power minus j omega naught t. Okay, so same thing has been kept here. So it is 1 by 2 ft and this. Okay, so now Fourier transform of ft cos omega naught t is equal to half is constant, so it is kept out. Fourier transform of ft to the power j omega naught t and Fourier transform of ft to the power minus j omega naught t. So now by using the modulation property, we can write the Fourier transform of this also. So 1 by 2 f of j omega minus omega naught and 1 by 2 f of j plus omega naught. Okay, f of j omega plus omega naught by using the modulation property. So now if you need to draw the spectra, so here see, this is the ft cos omega naught t. So here second example is that function has been considered as that it is varying from minus d by 2 to d by 2 and it is having value 1, and for rest of the time it is 0. Okay, so now this is the way here Fourier transform of this, we can write 1 into e to the power j omega t, limit will be only from minus d by 2 to d by 2. So this, by integrating this we can achieve this. Okay, so this is the Fourier transform, and f of j omega of this function into cos omega naught t, it will be a shifted function. Okay, so as we had discussed here, first part will be shifted with omega minus omega naught and second part will be shifted with omega plus omega naught. Okay, so see here, see omega plus omega naught. So we can write omega plus omega naught into d by 2, and so now if you will have to draw the spectra, so this will be the spectra. This is the magnitude spectra because it is having two part. Okay, so sine d by 2 omega minus omega naught and sine d by 2 omega plus omega naught. So this is the complete spectrum, continuous magnitude spectrum. Okay, and second example is the next example is that ft is sine at upon pi into t. So what will be the f of j omega? Okay, so you can proceed as solution is also given. So this is the way that we can calculate Fourier transform of this. Okay, so next is that Fourier transform of f dash t, that means d by dt of ft. Fourier transform of ft is f of j omega. Then what will be the Fourier transform of d by dt of ft? Okay, so here we should remember that Fourier transform of d by dt of ft will be j omega into f of j omega if Fourier transform of ft is f of j omega. So this is the proof. Okay, so here Fourier transform of f dash t. So here f dash t into e to the power minus j omega t dt, we will integrate this from minus infinity to infinity. Okay, so now if you will apply Fourier, if you apply integration by parts, you will be having this and this. So now after keeping the limits, you will get only j omega into f of j omega only. Okay, So this is the generalized form property of the Fourier transform for differentiation. So d by dt of, okay, suppose this is the function. Okay, so Fourier transform of this will be j omega to the power n f of j omega. Okay, so this is the integral property. Okay, so integration Fourier transform of ft is f of j omega, then Fourier transform of integration of ft is 1 upon j omega f of j omega. This is the proof. Okay, so I had discussed already various proof, so you can understand this as well. So this is the derivative of Fourier transform. Okay, so see here, so function ft is being multiplied with minus j into t. Okay, so then Fourier transform of this will be d by d omega of f of j omega. Okay, so this is the proof that already discussed. Okay, so this was all about the properties of Fourier transform. So next, in next discussion, you can see more videos on Fourier transform, where we will apply this Fourier transform in solving the equations. Okay, in finding the solution. Okay, we will analyze, as we discussed, that we use Fourier transform for analysis and we use Fourier integral or inverse Fourier transform for the synthesis part. So in next lecture you will find application of Fourier transform for circuit analysis. Okay, thank you all.